What specific problem does the speaking with intent (SWI) method aim to solve in the context of enhancing large language models (LLMs)?
The speaking with intent (SWI) method aims to solve the problem of enhancing the reasoning abilities of large language models (LLMs) by enabling them to explicitly articulate their own intent during the generation process. This approach addresses the limitations of traditional intent modeling, which typically relies on predefined categories, by allowing LLMs to generate free-form intent statements that guide their problem analysis and logical reasoning. By incorporating intent as a planning mechanism, SWI facilitates a structured thinking loop similar to human reasoning, thereby improving the quality of generated outputs across various tasks, including mathematical reasoning, multiple-choice question answering, and text summarization. The method has been shown to outperform baseline models that do not utilize intent, as well as other prompting methods like chain of thought (COT) and analyzing, retrieving, and reasoning (ARR). Overall, SWI enhances task performance and output explainability by providing high-level guidance for subsequent analytical steps.
How does the proposed speaking with intent (SWI) method work? Please illustrate the process step by step, focusing on the role of intent generation in guiding LLM reasoning.
The proposed speaking with intent (SWI) method works by requiring large language models (LLMs) to explicitly articulate their intent during the problem-solving process. This process begins with the LLM generating a high-level intent statement that serves as a guiding framework for subsequent analysis and reasoning. Each analytical step in solving a problem is then directed by this intent statement, allowing the model to follow a structured thinking loop similar to human reasoning. Specifically, the LLM generates intent as free-form text rather than predefined categories, enhancing flexibility and fluency in its reasoning. This iterative and dynamic generation of intents not only improves the quality of the output, but also enhances the model's ability to analyze and solve complex problems effectively, as evidenced by superior performance in various tasks compared to baseline methods.
Can you provide a simple yet illustrative example demonstrating how the SWI algorithm operates in a specific reasoning task, and explain each step involved?
The speaking with intent SWI algorithm operates by requiring the LLM to articulate its intent before solving a reasoning task, such as a mathematical problem. For instance, in a math problem, the LLM first generates an intent statement like, "I need to identify the key variables and the operation required to solve this problem." This intent guides the model's subsequent analysis, leading to a structured reasoning process where it might state, "Next, I will extract the numbers involved and determine the mathematical operation." Following this, the LLM performs the calculation, articulating each step, such as, "Now I will add these two numbers together." Finally, it concludes with a final answer statement, ensuring that the reasoning process is transparent and coherent. This iterative approach, where each analytical step is preceded by a generated intent, enhances the model's problem-solving capabilities and output quality, as evidenced by improved performance metrics in the experiments conducted.
What are the theoretical or practical benefits of implementing the SWI method compared to existing approaches such as chain of thought, COT, and analyzing, retrieving, and reasoning, arranged by?
The implementation of the speaking with intent SWI method offers several theoretical and practical benefits over existing approaches like chain of thought, COT, and analyzing, retrieving, and reasoning, ARR. Theoretically, SWI enhances LLM reasoning by allowing models to articulate their own intent, which serves as a guiding framework for problem solving, thereby replicating a structured human reasoning process. Practically, SWI consistently outperforms COT and ARR across various benchmarks, particularly in mathematical reasoning tasks, where it surpasses ARR in solving competition-level problems. Additionally, SWI improves the quality of outputs in text summarization by generating more accurate, concise, and factually reliable summaries with fewer hallucinations. Human evaluations further confirm the effectiveness of SWI, showing high coherence, effectiveness, and interpretability of the generated intent, particularly in mathematical reasoning tasks, which indicates its superior performance in guiding analysis and reasoning compared to traditional methods.
How was the effectiveness of the SWI method validated in the experiments? Please detail the datasets used, the metrics for performance evaluation, and any benchmarks it was compared against.
The effectiveness of the speaking with intent SWI method was validated through extensive experiments across various datasets, specifically focusing on mathematical reasoning, multiple-choice question answering (QA), and text summarization. For mathematical reasoning, datasets included GSM-8K, GSM-8K Platinum, Math 500, and competition-level benchmarks like AMC23, AME24, and AME25. The performance was evaluated using metrics such as exact match for mathematical tasks, option selection for multiple-choice QA, and Rouge scores for summarization tasks. SWI was compared against several benchmarks including baseline generation without intent, chain of thought (COT), plan and solve (PS), and analyzing, retrieving, and reasoning (ARR). Results showed that SWI consistently outperformed these methods, with an average improvement of +334 points over baseline in mathematical reasoning and +1008 points in multiple-choice QA, confirming its efficacy in enhancing reasoning and generation quality.
What limitations or drawbacks does the SWI method present, particularly in its application across different reasoning tasks or in terms of complexity?
The speaking with intent SWI method, while effective, presents certain limitations, particularly in its application across different reasoning tasks. One notable drawback is that in multiple-choice question answering (QA) tasks, the number of generated intents is often limited to 1 or 2, which may hinder the depth of guidance compared to the 3 or more intents typically generated in mathematical reasoning and summarization tasks. This limitation suggests that the effectiveness of SWI may be less pronounced in QA scenarios due to the lack of multi-step guidance. Additionally, while SWI improves performance, the human evaluation scores for QA tasks were relatively lower compared to those for math reasoning, indicating that the method may not fully leverage its potential in more complex reasoning environments. Furthermore, the reliance on the iterative generation of intents may introduce complexity in ensuring coherence and effectiveness across diverse tasks, which could affect the overall interpretability of the generated outputs.